All right, you have to bear with me. The paper that I have is printed on the other side, so you'll kind of see some lines in here. But today we're going to talk about radical expressions. If you looked at the syllabus, it says rational expressions. We're actually going to hold off on the rational expressions. We're going to do radical expressions. Okay, radical expressions. So what is a radical? A radical, you may remember, is something like this, a square root sign, square root of 9. Okay, that is 3. But this symbol right here, called a radical. Okay. And there's all kinds of different radicals, not just square roots. There can be what are called cube roots. Okay. Cubed root of 27 is 3. That means that 3 times 3 times 3 is 27. Square root of 9 is 3. That means that 3 times 3 is 9. So if I have 3 squared, it's 9. If I have 3 cubed, it's 27. So the cubed root of 3 cubed is 3, and the square root of 3 squared is 3. So the exponent and the root are inverse functions, just like plus and minus, just like multiply and divide. We have an exponent and a radical. Those are inverse functions of each other. Now, we can actually denote the square root of 9, okay, as an exponent. I can write 9 to the 1/2 power. 9 to the 1/2 power. That's the same thing as the square root of 9, or 3. The cubed root of 27, let's say, I can also denote as an exponent. Okay. 27 raised to the 1/3 power. That's the same thing as the cubed root, or in this case, 3. So a radical is the inverse of exponent. So if we think about 5 plus 5, that's equal to 10, or it's equal to 2 times 5, right? We're adding 5 twice to 2 times 5. If we think about 5 squared, that is 5 times 5, 25. If we think about the square root of 25, we're looking for two identical things that multiply by each other to get this number, 25. Square root of 25 is 5. Another way to write square root is 25 to the 1/2 power. That's the same exact thing as square root of 25. So x to the second power, sorry, the square root of x is equal to x to the 1/2 power. The cubed root of x is equal to x to the 1/3 power. The fourth root of x is equal to x to the 1/4 power. The fifth root of x is equal to x to the 1/5 power. They mean the same thing. So your exponents have just been integers up until this point, right? Remember, integers are, they're the natural numbers, 1, 2, 3, so on and so forth. It's also the whole numbers, so 0 can be in there, and the opposite of the natural numbers. So -1, -2, -3, so on and so forth. Those are integers, if you remember from our first class. And those integers are all that you've seen as exponents. But now we're looking at rational integers. We're looking at numbers that are rational, that can be expressed by the ratio of two integers. Okay. So now I want to show you, here we will do 2 to the 2/3 power. How do I understand that? 2 to the 2/3 power. So what we're going to do here is we're going to have the bottom number is going to be the radical, and the top number is going to be the power. It's not technically the power, but I think for us to kind of understand how that kind of works. Okay, so 2 to the 2/3. Well, we know that 2 to the 1/3 is the cubed root of 2. Okay, we just covered that. 2 to the 2, you know that as 2 times 2. So we're actually going to put these two ideas together in 2 to the 2/3. There are two ways to write this. We can say the cubed root of 2 squared, or we can say the cubed root of 2 squared. Those are the same thing. Okay, we can do 2 squared, and we want the cubed root of that, or we can do the cubed root of 2, and we want that squared. Both of those are expressions of 2 to the 2/3. All right. So we're learning about fractional exponents. 4 to the 1/2 power is the square root of 4. Now, well, how come we didn't take that 1 into consideration? Well, we did. 4 to the first power and then square root of 2. The square root is the only root symbol that we don't write the type of root that it is, which is a 2, a square root. Every other root, if I did 4 to the 1/3, right, we would have a little 3 there, the cubed root of 4. 3 identical numbers that I multiplied together that gives me 4, which is not going to be a rational number, right? This will be a rational number. In fact, it'll be an integer. It'll be 2. 2 identical numbers. That's 2 times 2 is 4. So that has a clean answer. This one won't. The cubed root of this will be something pretty tiny. All right. So square roots. So let's talk about simplifying radicals. So let's look at the square root of 200, or what can be called 200 to the 1/2 power. Okay, means the exact same thing. How do I get that? So we can plug this into our calculator, which I'm going to teach you how to do this by not using calculators. But I'm doing this just to kind of show you. So if I did the square root of 200 and I hit enter, you see that big long number? It's 14.1421356730. And if my calculator had more digits, it would keep going. It's an irrational number. Okay? Irrational. This cannot be expressed by the ratio of two integers. So, but what I can do is I can express this exactly. And the way that I can express this exactly is through a little simplifying. So right now it's expressed exactly. Square root of 200. This is an approximation, right? There are more decimal places out to infinity. So no matter how many decimal places I write, it's still only an approximation. This is an exact answer right here. So what I want to do is break this down to see if there's a way that I can um, make that a little bit simpler. So we're going to use this particular concept, okay? And that is that if I have the square root of two numbers that are multiplied together, okay? Two numbers multiplied together and they're under a root, that's the same thing as the root of the first, or the square root of the first, times the square root of the second. Okay, and vice versa. If I have the square root of a times the square root of b, that's the same thing as the square root of a times b. So I'm going to use that. Let me show you how. I can break 200 into 100 times 2. And the reason that I want to do that is because I notice here that 100 is a perfect square. The square root of 100 is 10. Okay, so what I'm going to do is I'm going to take this square root of 200 and I'm going to express that as the square root of 100 times 2. So notice that I haven't changed anything. Both of these are the square root of 200. I've simply taken the 200 and I have expressed it as 100 times 2. So here we have 100 times 2. Now I'm going to use this principle here that I just taught you. So we have the square root of 100 times 2. So I can split that, those two, I can split into their own individual radicals. So this becomes the square root of 100 times the square root of 2. Okay? The square root of 100 is 10, and then we have times the square root of 2. So the square root of 200, or we can write the square root of 200 this way. The square root of 200 is 10 times the square root of 2. And that's also an exact answer. The square root of 2 is an irrational number. And so we're going to write it exactly, which is the way that we have it there, which is square root of 2 times 10. So this is a simpler expression than square root of 200. And that's how we kind of simplify that. Okay? And it's using this idea. The idea that the square root of a times b is equal to the square root of a times the square root of b. All right. All right. Double check something in my notes real fast. I'll make sure I don't miss something. And I forgot to bring my notes up. Okay. So let's do this. Let's do 36 times x squared, square root of that. Or what we could write as 36 times x squared, quantity to the 1/2. Okay. All right. So we're going to take our same principle that we learned, and we can split this into two radicals. Square root of 36 times square root of x squared. Square root of 36 is 6. Square root of x squared is x. So we actually have a perfect square there. 6x. All right. Now, let's look at doing it with some multiplication. So let's look at 3 times the square root of 5 times the square root of 5 plus 1. Okay? So a nice, easy distributive problem here. We have 3 times the square root of 5, and I'm going to go ahead and distribute this into this quantity because I have parentheses here. Okay? So 3 times the square root of 5 times the square root of 5. Right? Plus 3 times the square root of 5 times 1. So 3 times the square root of 5. Now here, notice what we have. We have the square root of 5 times the square root of 5. So we can use the principle that we looked at earlier in reverse. We said that if we had the square root of a times b, that's the same thing as the square root of a times the square root of b. But we can also apply that in reverse. The square root of a times the square root of b is the same thing as the square root of a times b. And that's what we have here. The square root of 5 times the square root of 5. Well, that can just be the square root of 5 times 5. Then here, plus 3 times the square root of 5. 5 times 5 is 25. 3 times the square root of 25. Plus 3 times the square root of 5. The square root of 25 is just 5. 3 times 5 plus 3 times square root of 5. So we can do a couple of things here. One, I can pull out the 3, and I could say 3 times 5 plus the square root of 5. Or I can just multiply these two together and get 15 plus 3 times the square root of 5. Both would be acceptable answers. We typically want to write it like this, though, just so that we separate the terms a little bit more. This is a little bit more common for the nomenclature. I don't have a good reason for why it's more typically done this way. We just know that it is. Okay, so that was multiplying. Now let's look at subtraction. Let's do square root of 3 times square root of 2 minus square root of 6. Oh, I did want to bring up one thing from this former one. I forgot to mention this. Notice here how I have the square root of 5 times the square root of 5 equal to the square root of 25, which is 5. So if the square root of 25 is equal to 5 and the square root of 25 is equal to the square root of 5 times the square root of 5, that means that the square root of 5 times the square root of 5 is also equal to just 5. And this is one of our principles, and that is that the square root of a times the square root of a is equal to a. And we can show that. Square root of a times the square root of a is the square root of a times a. The square root of a times a is the square root of a squared, and the square root of a squared is a. So when I have the square root of a number times the square root of the same number, it returns the number. Okay? And in the case of a cubed, if you had the cubed root of a number, let's say b, times the cubed root of a number b, times the cubed root of a number b, that would equal the number b. Okay, same idea. All right. So now let's look at this problem right here, some subtraction. I'm going to take my square root of 3 and multiply it here. That's going to give me the square root of 3 times the square root of 2. And then here, that's going to give me minus the square root of 3 times the square root of 6. All right, so we know if we multiply two square roots together, we can put the two numbers together. So this would be the square root of 3 times 2 minus, same thing here, square root of 3 times the square root of 6. That's square root of 3 times 6. So here we have the square root of 6 minus the square root of 18. All right, so here, my 6, if I break that down any further, that's just 2 and 3. Neither one of those are a perfect square. I can kind of leave that alone. This 18, right, that was my 3 and 6. But my 6 can also be divided into 3 and 2. So look here, I have a perfect square, 3 times 3, which is 9. 9 times 2 is 18. So what I can do with this square root of 18 is I can say 6 minus, and I can divide this square root of 18 into the square root of 9 times 2. And the reason that I'm doing that is because now I can do minus the square root of 9 times the square root of 2. And the square root of 9 is 3. And now I have square root of 6 minus 3 times the square root of 2. All right. So let's do 3 plus the square root of 2 times 4 plus the square root of 2. Okay. All right. So here we're going to do some distribution. Okay. We've got this whole block right here that we're going to multiply by this number, and we're going to multiply by this number. Okay. And when we do that, we're going to have 3 plus root 2 multiplied by 4 plus 3 plus root 2 multiplied by root 2. Okay, that's what I've shown here. Then when I multiply my 4 through, 4 times 3 plus 4 times the square root of 2 plus square root of 2 times 3 plus square root of 2 times square root of 2. So notice when I have two binomials that are multiplied by each other, I end up with 1, 2, 3, 4 terms, okay? So let me show you what that looks like kind of in a generic way. We have A plus B times C plus D, okay? Here, notice my 4 and my 3 are being multiplied together. That's the first term, okay? The first two terms, A times C. Plus, then I have 4 and square root of 2. That's these two terms right here. B times C. Then I have 3 times the square root of 2. So I have A times d. Then I have square root of 2 times square root of 2, which is these last two. So that's b times d. So this is kind of you can write down this property, but it essentially comes from the same idea of how we worked this out. Okay, so let me show you that again, more generic. So we're going to take this and we're going to distribute it through. Okay, so we have a plus b multiplied by c plus a plus b multiplied by d. Then we're going to distribute the c in. So ac plus bc plus, now we're going to distribute the d in, ad plus bd. So that's where that comes from. And I'll review this again when we look at factoring quadratics because that'll come in handy. But let's go ahead and kind of simplify this right here. So 4 times 3 is 12 plus 4 times the square root of 2. Can't simplify that, so we'll leave it alone. Plus 3 times the square root of that. Can't simplify that, so we'll leave that alone. And then square root of 2 times square root of 2, we looked at that before. The square root of a number times the square root of the number is the number, so plus 2. All right, so now we kind of have some like terms here. We've got two constants that we can combine, 12 and 2, both positive, so that can become 14. Then look at this. We have 4 times the square root of 2 plus 3 times the square root of 2. So those are like terms as well. And that would be plus 7 times the square root of 2. And that would be the answer. Right. All right. Now, let's look at what happens when we have something like this. All right, 1 over the square root of 5. So one of the rules in math is that we cannot have a radical in the denominator. We cannot have a radical in the denominator. And it's actually an interesting, I'm going to look up why real quick because there's nothing mathematically wrong with that, but let me see if there's an interesting. Okay, so it's just nomenclature. The reason is because radicals often, at least what I just looked up, radicals are often irrational numbers, and people would rather have those in the numerator rather than the denominator. So again, it's not like 1 divided by 0, which is mathematically impossible. That's actually an error on your calculator. This isn't an error, but it's not the correct way. So the correct way to deal with a radical, a square root, a cube root, or something like that in the denominator is to do the following. So we're going to use the same idea that we've used before, and that is that the square root of a number times the square root of a number gives us the number. Okay, so I'm going to take 1 over the square root of 5, and I'm going to multiply it by 1. Okay, if I multiply it by 1, then I'm not changing anything. But I'm going to express that 1 a little differently. Not just by 1, but I'm going to express 1 as the square root of 5 over the square root of 5. And the reason that I'm doing that is because I want the bottom to multiply out the radical. So now if I do 1 over the square root of 5 times the square root of 5 over the square root of 5, in order to perform this operation, we're multiplying two fractions together. So we multiply across the top. 1 times the square root of 5 is the square root of 5. Square root of 5 times the square root of 5 is 5. So now, square root of 5 over 5, that's the same thing as 1 over the square root of 5, but this is in the correct nomenclature because there's no radical in the denominator. There's no square root sign in the denominator. Okay? All right, so let's do another one kind of like that. Let's do one a little bit more complicated. Let's do square root of 10 over square root of 75. Okay, how would we do that? Well, square root of 10 in the numerator is no big deal, but we don't want that square root in the denominator. Now, there's a couple things that we could do. We could multiply the top and bottom by the square root of 75. That's fine. But what I do know is I can actually simplify that 75. So 75, that's the same thing as 25 times 3. And 25 is a perfect square. So actually, the first thing that I'm going to do is I'm going to leave this as the square root of 10 over, and I'm going to rewrite the square root of 75 as the square root of 25 times 3. Okay? The square root of 25 times 3. What that's going to let me do then in the denominator is I can split the radical over those two factors. Square root of 25 times the square root of 3. The square root of 25 is 5. So now what I'm left with is the square root of 10 over 5 times the square root of 3. Well, the 5 in the denominator is fine. There's no radical associated with that. That square root of 3, though, that's not good. Now what I'm going to do is I'm going to multiply the top and the bottom by the square root of 3, or essentially I'm just multiplying this times 1. Square root of 3 over square root of 3. And that is a lot simpler to me than multiplying top and bottom here by the square root of 75. So I always look to see if there's a way to simplify before we're doing this. So the square root of 10 times the square root of 3, I can put that underneath the same radical. Square root of 10 times 3. And then here in the bottom, I have 5. Square root of 3 times square root of 3 is 3. All right. 10 times 3 is 30. So I have the square root of 30 over 5 times 3 is 15. All right, is there any perfect squares in 30? If I take 30 and kind of factor it, that's a 3 and a 10, as we well know. And then the 10 is a 2 and a 5. So I don't have any perfect squares there. There's nothing I can really do. So this is my simplest form of that. Square root of 30 over 15 is the square root of 10 over the square root of 75 in proper notation. Right. Now let's do square root of 2 plus square root of 5 over square root of 10. All right, so what do I do here? All right, so the square root of 2 plus the square root of 5 in the top is no big deal. That can be in the numerator. And I really can't simplify either one of those. The square root of 2, square root of 5, both are prime numbers, so they don't have any factors. 10, the two factors are 2 and 5. Neither one of those are perfect squares. So what I need to do here is get rid of that square root in the denominator. So how do I do that? I'm going to multiply the top and bottom by the square root of 10. Now remember that this is a vinculum, okay? Meaning that it implies that there are parentheses above and parentheses below. Why is that important? It's important because we're going to multiply these together. So the denominator is easy. Square root of 10 times the square root of 10, that's just 10. But here, we want to do, this is a quantity, so I need to distribute this because I have two terms in here. So I have to distribute the square root of 10 over the terms. So I have the square root of 10 times the square root of 2. Plus the square root of 10 times the square root of 5. I just noticed I said it one way, then wrote it the other way. It's because you can multiply in any order you want. So if you said square root of 10 times the square root of 2, that's fine. Plus square root of 10 times the square root of 5, that's fine. Okay, now I'm going to combine these under the same radical, 2 and 10. So square root of 2 times 10 plus square root of 5 times 10 over 10. All right, so now I'm going to multiply. 2 times 10 is 20. Square root of 20, whoops, 20, plus 5 times 10 is 50, so square root of 50, all over 10. All right, now let's see if I can get any square root of 20. Do I have any perfect squares in there? All right, so 20 is going to be 10 times 2. 10 is going to be 5 times 2. I do. I've got two 2's in there. I've got a 4, in other words. 4 times 5. So that'll be what I will do with the 20. Then if I look at the 50, and I divide 50 by 10, I get 5. 5 times 10. And then this is also 2 and 5 here. So notice I've got two 5's. 5 times 5 is 25. So I've got a 25 and a 4. Both of those are perfect squares that will be underneath radicals. So the square root of 20, I'm going to rewrite as this, so it has my perfect square, 5 times 4. Plus, then I'm going to do this for the perfect square. And that is the square root of 2 times 25, all over 10. All right, now I can split the radical over those two that are being multiplied. Square root of 5 times the square root of 4 plus square root of 2 times the square root of 25, all over 10. All right, the square root of 5 is our near rational number. It's a prime square root. That just stays there, but the square root of 4 becomes 2. So 2 times the square root of 5 plus square root of 2, same thing, just remains square root of 2. And then square root of 25, that just becomes 5. So plus 5 times the square root of 2, all over 10. And you're done. There's nothing I can factor out of here that would cancel with anything below. Even though this is 2 times 5, I'd have to factor out 5 out of both or 2 out of both, and I can't. So that is your final answer there. Right. All right, so now I'm going to look at 3 divided by 2 minus the square root of 2. So this one's a little bit different. This has a radical in the bottom, but only one of them has a radical. The other one doesn't. But the same principle is going to apply. So this is going to be a little complicated because if I come in here and I multiply the top and bottom by the square root of 2, okay, the top becomes 3 times the square root of 2. And the bottom, when I distribute this, becomes 2 times the square root of 2 minus 2. So even though it took this radical away, and I'm just left with the 2, it reintroduces a radical here that I didn't have over here. This is kind of an issue. So we're going to use something called a conjugate. 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 What is a conjugate? All right, so a conjugate is a binomial whose internal sign has been reversed, okay? These aren't equal to each other, but they are conjugates. So look, A plus B, the conjugate is A minus B. If I have A minus B, the conjugate is A plus B. Now be careful with this because if I have negative A plus B, the conjugate is still negative A minus B. The only thing that we're changing is the sign in between, not the sign on the actual terms themselves. Okay, that's very important. All right. So what happens then with a conjugate, and so let's say that I have A plus B times A minus B, okay? So remember, I first have my first two terms, A squared, then I have the first and the last, minus AB, then I have the internals here, plus BA, and then I have this, B times negative B, which is negative B squared. I want you to notice something interesting. AB, negative AB, and positive BA, those are the same thing. We can multiply in whatever order we want. So I'll rewrite this to look exactly the same. Negative AB and positive AB cancel each other. And what you're left with is A squared minus B squared. By virtue of these two being squares, and the fact that the middle term drops out, I can use a conjugate to get rid of the radical in the denominator. Okay, so what does that look like? Well, I'm going to take this 3 over 2 minus the square root of 2, and I'm going to multiply the top and the bottom by the conjugate of the denominator. So the conjugate is 2 plus the square root of 2. And I'm going to do the top and the bottom, 2 plus the square root of 2. And just remember that vinculum means that there are implied parentheses. All right, so let's multiply across the top. 3 times 2 is 6. 3 times the square root of 2 is 3 times the square root of 2. Then here on the bottom, we already looked at what happens with the conjugate here. A plus B, A minus B, we have A squared. So that's 2 squared minus B squared. Square root of 2 times the square root of 2, that's just 2. Now, let's go ahead and prove that to ourselves, okay? because that, your brain needs to see why that is the case. So let's do 2 minus the square root of 2 times 2 plus the square root of 2. 2 times 2 is 4. 2 times the square root of 2 plus 2 times the square root of 2. Minus square root of 2 times 2 is minus 2 times the square root of 2. Minus square root of 2 times positive square root of 2 is minus square root of 2 times square root of 2. So what I'm left with is 4 plus 2 root 2 minus 2 root 2 minus 2. Positive 2 root 2 and minus 2 root 2 cancel, and I'm left with 4 minus 2, which is what I have here. 4 minus 2, which is just 2. So I have 6 plus 3 root 2 all over 2.